This is our very first video lesson in calculus. This is about can change occur in an instant? That's one of the huge ideas in calculus, is looking at the rate of change of a graph. So what we're going to do today is we're going to look at average rate of change, which I hope you've seen before in advanced algebra perhaps, in pre-calculus perhaps, and then we're going to try to look at that on smaller and smaller intervals so that we can start thinking about instantaneous rate of change. All right. So when I was in college, there was a clock, a countdown clock sort of thing in the science building, and it was showing the population at that time. And I remember when that clock changed to 6 billion people. Right now we're talking about by the end of this century, there will be somewhere around 11 billion people. And that is including the slowdown in birth rate. So when I was a kid, it was not at all unusual to have a family size of, well, my family size was 3 kids. That wasn't unusual. It wasn't unusual for there to be larger families either. At this point, that becomes more and more unusual as our average number of kids per family drops to closer to 2. In my own generation, it's hard for me to think of any families with more than 3 kids, and very few have even that many. So even with that, we see that our population is going to hit 11 billion before the end of this century. And it was 6 billion within my adult memory. So that's very fast rate of change. So what I wonder is, what was the rate of change of population size in 1800? That is before I was born. 1800 would be like right here. And so what is the rate of change at that instant? And this is, rate of change. We talk about that with straight lines, but this graph is not a straight line graph. So how do you figure out what the rate of change is? And then the other question is, what units does rate of change use for this particular graph? And so definitely I want you to know rate of change is slope. So rate of change for this particular graph, because rate of change is slope, it's going to be rise over run. So for this graph, the rise is the change in number of people. So the rise is going to be billions of people. And the run is going to be, time, so years. So the correct units for this particular graph, because rate of change is slope, would be billions per year. And so in 1800, and I'm kind of going to leave this kind of up to you to think about, but in 1800, one thing we could do is we could say, well, I don't know exactly what the rate of change is at 1800, but here's 1900, and I can estimate, like, this point right here is 1800, comma, looks like 1 billion. And this point right here is 1900, and it looks like 1.5 billion. So I could figure out the rate of change between those 2 points by using our slope formula. So I could say 1.5 minus 1 over 1900 minus 1800. And that's one way that I could figure out what is the rate of change in 1800. I could say, well, it's 0.5 divided by 100, so it's really 0.005. Is that enough zeros or too many zeros? 1, 2, too many zeros. Billion per year. But then what if your friend says, yeah, I like your method, that's fine, but that's not the way I would do it. The way I would do it is I would say, use this point right here, and this point looks like it's 1700, comma, I don't know, 0.6. So I'm going to use that point instead, and I'm going to get a different result when I do that. So your friend is going to choose to find the rate of change between those 2 points. And who's correct? Are either of you correct? Is there a better way to do it? And so that's kind of our question for today. But we certainly could get an estimate of it using either one of those 2 methods. Oh, I got to clear my screen. So here's another situation. When I was in college, it looks like the fossil fuels were like we had 22 gross tons of carbon dioxide emitted that year. And now it looks like we have almost 38 gross tons of carbon dioxide emitted a year. So what was the rate of change of carbon emissions in 1990 when I was a senior in high school? And what units does that rate of change use in this situation? So again, units are going to be rise over run. So if I look at the rise over run for this graph, rise is going to be global tons of carbon dioxide, and run is going to be per year. So that would be my units for the rate of change situation. And then in 1990, what was the rate of change? Again, I would look at 2 points that you can find and find the rise over run for 1990. And maybe if I choose those 2 points, that's fine. But maybe my friend is going to choose 2 different points. So it's not maybe going to be exactly the same depending on who's calculating it and what points they're using. But it's an estimate of what the rate of change is at that point. So just a reminder, average rate of change, which you've used before, is the slope. It's another name for slope. So if I want to know the average rate of change between A and B on my x-axis, then I would just subtract the y-coordinates and subtract the x-coordinate, and that would give me the average rate of change. You will be using average rate of change a lot, and I'd like to warn you that in this class, if I say the word average, I will never, ever, ever, ever be asking you to add up a bunch of items and divide by how many you have. I will not be using the mean in this class. I will also not be using the median in this class. I will, however, be using average rate of change quite a lot. So when you hear those words, you should be thinking slope. We are going to start thinking about, and this is new to you, I hope, instantaneous rate of change. We want to know the rate of change at an instant. For a linear function, we've done this because the rate of change doesn't change, right? So at any instant, the rate of change is the same. But for curvy graphs, like those real-world situations I was showing you, we would like to figure out what is the instantaneous rate of change. So we want to use the slope formula, but if it's instantaneous, we're not going to have 2 points. We just want to have a single point. So the problem is, if I have the slope formula at a single point, that's fine, except everything turns out to be 0 over 0, and if there's one thing I know, it's that dividing by 0 is going to break math. So 0 over 0 is a problem, and right now we're going to leave it there, that it's a problem. And that's going to be our goal of how are we going to solve this problem of 0 over 0. We don't want to break math, but mathematicians, they have a trick. When they're about to break math, they invent more math, and that's what calculus is. All right, here's our summary for today. Average rate of change is the slope. If you hear those words, average rate of change, you should be thinking slope. We can estimate the instantaneous rate of change by calculating the average rate of change with 2 points that are close together. It's an estimate, it's not exact, but we can do that. At a single point, the slope formula is giving us a slope of 0 over 0, and we recognize that that's a problem, and we're going to need more math in order to get out of that problem. So that's where we are.